Well, it's a pleasure for me to be here. As was mentioned, I'm a faculty at Johns Hopkins University. I don't think the School of Advanced International Studies is not serious. In fact, arguably, international studies is much more serious than what I do anyway. But it's an honor for me to be here, and hopefully next year I can be there in person. So I'm going to be speaking about learning the next frontier, and this is a recent work of ours. It's going to be published in a couple weeks, actually, at a conference called NeurIPS, which is basically the premier AI conference these days. And so what I'm going to tell you about is something that we call learning. All of us kind of have some idea of what it is, but I'm going to teach you my perspective on it, and then how we get it, how do we model it, what's wrong with our model, how we fix it, and what do we do. And it's a very brief overview. If anybody has any further detailed questions, I'm happy to talk afterwards or communicate in other ways. So I want to start by showing you this video. This video is going to be of a single cell organism, that's image here, and you're going to see it's hunting.
This is Polycricos caffoidi, hunting for dinner. We've known.
I don't know if you could see that. I'm going to play it again. And you'll see it has a little torpedo, and this big one shoots this little one, and then it takes it away.
This is Polycricos caffoidi, hunting for dinner.
So that's hunting. That's a single cell organism. Single cell organisms don't learn very much during their lifetime. They kind of learn across lifetimes. But still, it's not like when the universe was created, these things existed and knew how to hunt. Rather, over many evolutionary life cycles, they evolved this capacity to be able to find food, shoot this little torpedo at them, and then take them away.
This is
So that is one example of something that is learning. Here's another example. This is a Ninja Warrior course for a squirrel.
Ideas. So here's a single camera.
And what you see is on the right, the squirrel is climbing up, and the squirrel's been practicing this now for several weeks. And the goal for the squirrel is to get over to the bottom right where there's nuts. And the squirrel has learned it. In fact, there's a bunch of squirrels, they've all learned it together. And some of them learn by trying things, some of them learn by watching the other squirrels doing it. But the point is, obviously, this is learning at a very different scale from the scale that the single cell organism had. This is the guy who set it all up. He's a former NASA engineer. He's got a manual override for safety. But the point is, these squirrels learn all these things. They learn how to jump, they learn how to navigate, all kinds of good stuff like that. Now, here's a human.
They're just going to power through it. It doesn't work. Your brain cannot handle it.
This human is trying to ride a bike with something called flipped handlebars. So the deal here is that the handlebars, when you turn left, it turns right, and when you turn right, the wheel turns left. So it turns out once you've learned how to bike, it's extremely difficult to figure out how to do this, and it takes weeks and weeks of practice. This is a YouTube video. This guy travels around the world, embarrassing people by bringing them on stage, and they all think they should be able to do it, and they all fail miserably. Okay. So with that in mind, I'm going to tell you about what I think the deal is with biological learning. It's essentially the ability to use the past to improve future performance. And it evolved because the past is related to the future, though it's distinct from it. And this is really the key. In AI, which everyone now knows, real learning. It's a model of a natural phenomenon. And it turns out in machine learning, there's many different forms of formalizing these conceptual ideas into math. One of them is called probably approximately correct learning. It's the most prevalent one, PAC. Another one is called online learning. Another one is reinforcement learning. You may have heard about this. It's what people like OpenAI is using to help train their large language models. And the deal is what we know from, say, 100 years of statistics, that this famous quote, all models are wrong, but some are useful. And so that is true for all these models of learning as well. In fact, the leading AI model of learning, which most people are not aware of, comes from this paper from the 30s a couple of Italian guys, Clavenco and Cantelli, and the main result, I can't read the Italian, but I can read risulta, and the main result is this equation. And what this equation means is the estimate of this distribution of your data minus the truth. That difference is smaller than epsilon, which is a small number. So what they were able to prove is that if you have enough data, you can estimate basically anything you want. And that's kind of the intuition and the leading efforts behind OpenAI and DeepMind. Their whole vision is just get more and more data and be able to push that data through big arrays of GPUs, and we'll be able to estimate whatever we need to do. In fact, they claim we'll be able to estimate things like artificial general intelligence. I think that's completely wrong, but the point is they are making lots of progress, and you can estimate quite a bit if you have enough data. However, as I mentioned earlier, all models are wrong. So this model, which is 100 years old, is wrong, profoundly wrong in two particular ways. One of which is it assumes the data are what's called IID, identical and independently distributed. What that means is the future is assumed to basically be identical to the past. So if things are scattered around the room and messy one day, in the future, it should also be scattered around the room and messy. The other big assumption is that the goal is fixed, so that everybody has the same goal throughout, say, their entire lifetime. Of course, this is not true. When I'm a baby, I want someone to change my diaper and give me milk. Now that I'm an adult, I don't want either of those things. When I get later, I might want those things again. So the goals are changing in time, and the data are changing in time. However, pack learning, which is the workhorse and has been used incredibly usefully for the last decade to generate the whole new evolution of AI, is profoundly wrong in multiple ways. So why might you care about that? Well, there's a couple of reasons. One is this thing. So here's an example from Google Flu. Google, as you know, has probably more computers than anyone in the world, more data than anyone in the world. And they believe that they will be able to predict cases of the flu better than anyone in the world, in particular in the US. Now, what they did is they used queries of who was searching for questions about the flu on Google, and they tried to predict it better than the CDC, the Center for Disease Control in the US. This plot shows on the x-axis is time. It goes from 2009, they stopped training it in 2011, and then they deployed it for the next 2 years. The y-axis is the error. So you want the errors to be small, close to zero, and it goes up to 150%. Now, what you can see from this plot, the orange line is Google, and Google was almost always biased. After it was deployed, it tended to think there was more flu than there was. And in particular, its bias was quite bad. Its error was way over 100% often. This is in contrast to something called the lag CDC, which is essentially the simplest model in the world. You just say whatever happened last week will likely also happen this week. Okay, so now you have the most advanced AI company in the world with the most data and the most computers doing really profoundly poorly relative to the most trivial thing you could possibly do. So this is an example where AI just doesn't work. And it's not the only example. There's many, many examples like this, but this was a profoundly embarrassing one for Google. Another reason you might care is because I would say intelligence is what makes us us. We call ourselves Homo sapiens. That means thinking humans. So for me, understanding what it means to think and to learn is really a part of understanding myself and all of us. So here's the leading theory. It's called probably approximately correct. And Leslie Valiant, who wrote this book about a decade ago, he's one of the, say, godfathers of AI. He published some of the original work. He's profoundly well respected and deservedly so. He's a brilliant visionary. This book is said nature's algorithms for learning and prospering in a complex world. And my argument to you is these are not nature's algorithms. They're not even really very close to nature's algorithms because the fundamental driving assumptions of this work are just wrong. I want to say them being wrong isn't all bad. For example, Newton was completely wrong about the laws of physics, and yet Newton's laws are an incredibly good approximation for a large part of our daily lives. So being totally wrong isn't all bad. It's just a fact whether he's got the fundamentals right or not. And I would say that the vast majority of the AI community has the fundamental notion of learning completely wrong. Here's an example that's close to my heart, which is in our most recent paper, where we show a very, very simple thing that AI algorithms utterly fail at. And the deal is essentially there's two tasks. So task A could be, say that numbers bigger than 0 are positive and numbers smaller than 0 are negative. And task B, it's the opposite. So you say numbers bigger than 0 are negative and numbers smaller than 0 are positive. Now, if you give an AI algorithm, say 10 samples from A, and then 10 from B, and then 10 from A, and then 10 from B, what will happen is it'll just never learn anything or get everything wrong, because it has no notion of time. In particular, it assumes the future and the past are the same. But that's not true here. Whatever happened in the last 10 trials doesn't actually tell you very much about what will happen for the next 10 trials. So this figure on this axis, what I'm showing here is that time is on the x-axis and which task you're in is here. So it goes from A, B, A, B, A, B, switching every 20 samples. And in this plot, I'm showing a general measure of error over time. And there's a bunch of different algorithms. The main thing I want to tell you is all of these algorithms, the green, the blue, the purple, these are state-of-the-art AI algorithms. Now, like the last few years, there's been papers published on them in the top journals and conference venues such as NeurIPS, where our paper is published. And you can see their error, their instantaneous risk, is at 0.5 or oscillating between 0 and 1. 0 is the best you can do, and 1 is the worst. So these algorithms are either doing nothing or really worse than chance. The red line is our line, our algorithm, where what we did was we said, actually, you can try to predict the future. If we just give the algorithm another input, which is explicitly time, then it can learn the temporal dependence of the tasks. And it can figure out that, oh, at time 20, it's going to switch. And now I know that it's going to be task B for the next 20 seconds. And then the next 20 times, it'll do the same thing. So it can learn the temporal dependencies, even though other algorithms can't, because they don't have any notion of time in them. When we do that, what you can see is the red line, after about 250 trials, it never makes another mistake. So it learns the relationship of time and the tasks, and it makes no mistakes for the rest of the time, whereas the other algorithms will continue doing as bad as possible. So this is a proposal, our proposal, a new model of learning. It's based on the previous work, obviously, and there's lots more work to do. We take time seriously, which is important, I think, in many real-world examples, but we don't have algorithms at scale. We haven't really applied it to real data. We're just exploring these ideas now. So if anyone is interested in this, we're always hiring and looking for people to join, both at the graduate school level, but also in collaborations. We license our technology and the serial founder. So there's always good stuff to do together, regardless of your current industry or background. And the work was done by a number of students. Ashwin is the one circled in red. He was one of the main leaders of this work. And of course, I'm super grateful to my wife and my children, who are why I do all this stuff, because I love them and I want to live in a world where it's safe for them. Thank you so much.
So thank you very much, Joshua, for this. We are going to continue with a panel, but because it's hard to get questions over the video, we'll just do it a little bit differently. If anybody has a question for Joshua, maybe we can do it now before we start the panel. So I think that this presentation is, when I first started talking to you, Joshua, I was flabbergasted with a completely different approach to how you discuss AI than everybody else. And I think we have a speechless audience, but maybe not speechless enough that they have questions. Here we go, Johannes.
Hi, Joshua. This is Johannes. I'm totally flabbergasted, especially about the way you approach risk. And the question that immediately came to my mind is, have you tried variants A and B? with a distinctive set of a behavior. Have you tried that in a multiplicity of variants? Because we started doing that a time ago, and we came to the most funny results that we took ages to interpret and to understand. And even the behaviors that you had with the A and B as an input factor, maybe you want to tell us a little bit about that.
So let me make sure I understand the question. You're saying, have we tried with different, where there's more tests or the tests are more different and things like that?
Yes.
Yeah, sure. So in the paper, there's like 5 or 6 other experiments where we have 4 tests and they're cycling, or it's not deterministic which test it's going to, it's probabilistic, and that's governed by a Markov process. So you don't know exactly which test will be next, and the results all hold. Like our algorithms, we also have a theory, we prove that our algorithms will converge to the best possible thing that you can do, and that everything else won't. And that's what happens. The other things don't really work, and we converge pretty quickly.
Wow.
Anybody else?
Hey, thank you so much. This explains a lot to me, because we've been playing around with questions about how to estimate and understand risk in responsive behaviors, and so that felt really familiar. It's a very, very interesting topic, and I have to admit I especially like the way you display it, because I don't know how it is for the rest of the audience, but it comes over very clear, and for us it felt difficult to even elaborate on the question for more than a year. So thank you very much for that.
Thank you.
Anybody else? Any other? Oh, there's another question.
In terms of learning for the human, important motivation is a reward and punishment, or actual reward or actual punishment, or expectation of a reward or punishment. So that is the huge or fundamental motivation of learning, but machine doesn't have a reward or punishment, right? So how isn't it necessary to have matters or knowledge to gain useful for the survival? How does it apply to the human learning or machine learning?
Yeah, it's a great question. And I think, one of the issues with this kind of thing is the way that people use learning. We describe many different things as learning, and they're really quite different biological phenomena. So for example, imagine learning to play tennis. You just hit a ball over and over and over again. There's no explicit reward or punishment. You're just practicing, and eventually you get better. Or another example is lifting weights. You lift weights and, again, there's no real reward, but you get stronger. And so I would argue in both those cases, we're learning. In one case, we're learning how to play tennis. The other case, we're learning how to lift weights. And there's really been no explicit external rewards. So you can also learn just by watching somebody, right? The squirrels, I didn't show you this part of the video, but sometimes one squirrel does something and the other squirrel just watches and it's learned. It's called imitation learning. Babies do this all the time. It's how they learn how to smile and all sorts of stuff. So I would say generally you don't necessarily, as humans or animals, need an explicit external reward to learn. I would also say there's ways to encode reward and punishment into machines. Like the algorithms, you can give them feedback and say, oh, this was an error, therefore you should change things, or this wasn't an error, therefore you should do it just like that again in the future. So I guess my answer is it's very complicated how to think about reward and punishment for machines or animals in terms of learning. But I think there are equivalences that one can encode that into the algorithms.
Okay, we have another question, but go ahead.
Yeah, Professor, can I add one more element to that, which is the human trait on curiosity? We all have the sense of curiosity, which motivates us to learn. There's no way to inject that element into machine learning, right?
Oh, Well, so reinforcement learning is a field of machine learning where curiosity is basically built in. So there's a trade-off between what's called exploration and exploitation. And the deal is you can write an algorithm so that sometimes, rather than doing the thing that gets it the reward, it explores the environment more. And the optimal trade-off is dependent on, you know, what you want and the distribution of the world. But what I would say is people aren't very good at writing algorithms to do it well. The reinforcement learning algorithms take like orders of magnitude more trials to learn things that, you know, animals can learn very quickly. But there are ways of building in curiosity, and people are working on that.
So that was a question from Sridhar, and actually I was going to go another direction. Both you and Sridhar do a lot of work on human consciousness, and I don't know if you wanted to say a few words of how you tie your work and your work on consciousness.
Sure. Yeah. So, I mean, what I think about human intelligence and human consciousness is the core of it is really learning. If you think from an evolutionary perspective, one of the very first things sentient life had to figure out was learning, because that means you could do better in the future than you did in the past. And so for me, the sentience builds on top of the fundamentals of learning. And so if we don't understand like the core principles of learning, I think there's no way we're going to get to understanding consciousness. So for me, this is a route to getting to where we want to go, which is really understanding consciousness and supporting people to have deeper levels of consciousness so that we can eliminate suffering and increase flourishing in the world.
Thank you very much, Joshua.
Thank you. Thanks for the questions.